In physics, we know that power is the rate at which work is done. Or in other words, power can be expressed as work divided by time. Anytime our definition is the rate at which something is done, it always refers to being a quantity divided by time. However, this equation, which is one that we've used in the past, only works for the average. In other words, this is what we'd want to use when force is constant. However, we know force is not always constant. Therefore, we're going to have a slightly different definition of power in AP Physics. Specifically, when we have a non-constant force, our instantaneous power, similar to instantaneous velocity or instantaneous acceleration, can be expressed as the derivative of work with respect to time. That's one way of calculating the power. And this will work regardless of whether or not your force is constant. Again, this is instantaneous, which means it gives us the power or the rate at which work is done at a specific point in time rather than over a time interval. Now, this can also be expressed in another way because we know that work can be expressed in terms of the force on an object. Specifically, we can say that it's f dot dr, right? Or rather the integral of f dot dr. So we could take the derivative, d dt, of this expression. Now, if we happen to have a constant force, then really what I'm doing is taking the derivative of f dx times the cosine of theta, or the angle between my force and my displacement vector. Well, guess what? If I were to kind of combine these, write these in a different order, that gives me f times dx dt times the cosine of theta. Now, we know that dx dt is really a different quantity because we've learned previously that velocity can be expressed as dx, right? So that means another way of finding power, and again, this depends on when we have a constant force. So this can only be used if you have a constant force, is f dot v. Because remember, when we have the magnitude of one force times the magnitude of another, the magnitude of one vector times the magnitude of another vector times the cosine of the angle between them, that's really just the dot product. So either of these two equations, power is dw over dt, or power is f dot v, can be used for calculating power, or again, the rate at which work is done. Thinking about the units would be the units for work divided by the units for time, or joules per second. Or if we look at this power equation where it's F dot V, that would be Newton meters per second. But instead of writing this as joules per second, or Newton meters per second, we write it with a new unit called watts, whose symbol is a capital W. Okay, let's try it out with an example problem. In this problem, we have a machine carrying a 4-kilogram package. It gives us its initial position and its final position. It does so in 12 seconds. It says that there's a constant force applied by the machine on the package, and we're given that force as well as those position vectors in unit vector notation. There's two things we're looking for: the work that's done on the package by the machine's force and the average power. So for starters, since we're given things in unit vector notation, I'm going to calculate this. And again, also because it's a constant force, I can write work as F dot delta R. I'm using delta R here rather than delta X since we do have a three-dimensional displacement here. Let's write out what those two vectors are equal to. Because the force is 2I hat plus 4J hat plus 6K hat. And we have to figure out that displacement vector. Remember, displacement is final minus initial. So if I subtract this final position minus initial position, I find that to be 7I hat minus 11.25 j hat plus 7k hat, right? Okay. So finding the dot product when you have things in unit vector notation is relatively simple because all I need to do is multiply the x components, multiply the y components, multiply the z components, and then add together what I get. In other words, I'm going to multiply 2 times 7 plus 4 times negative 11.25 plus 6 times 7. When I do all that math, I find that my number is approximately 100 joules. So this does 100 joules of work on the package, the machine's force does. When it's asking for average power, there's multiple ways we could find that. But really, since it's average, we're going to go the simplest route, which says that power is the work divided by the time. Or 100 joules divided by my time, which is 12 seconds. Plug that into a calculator, and I find that the average power is 8.4 watts. We'll practice some more with power in the coming days.